Very good afternoon, everyone. So, welcome back after another important discussions in the last week. Last week, if you last lecture we have talked about insertion in B-tree. Very interesting process, very logical and very smart way of doing. Very interesting, I'll say. And from disk read issues we have done smartly, and disk read also handled smartly. So I'm sure all of you have done that, and you are able to understand the importance of a disk read minimization and at the same time split, etc. We have already discussed those. We have also talked of some programming aspects of this. So let's quickly just have a look on the programming aspect of the same. Partial code I'm going to share with you for the deletion, for the insertion case. Searching, we have already discussed this code sometimes earlier, before the previous class. Now here comes the insertion. So this is a first routine, which will effectively do the preliminary work. If the root is to be split, that a splitting of the root will be done. So effectively, here I'm doing the splitting of root before going down, if needed. And in single pass, we will be able to. So this split is always done in advance, so that later if shifting or median is needed, then that gets handled. So first time primarily we are doing it that if the current root has less than 2t minus 1, insert non-fill straight away. If the root is full, so root full will mean, of course, extra root created. Root's current node becomes the current root, and then I will call the split child. This node is full, so the split child will be called. If I want the level order traversal for verification, this you can do. Otherwise, after split child, we have to do the insertion call. So insert non-full, because now the S is non-full, or I have the child available with the corresponding S as a root, then it has got non-full node. So from here, effectively, that logic comes, which we discussed as insert logic. You can see here, not big work being done, except root being handled and root split if being handled, and root split also being handled via split child module. Insert non-full. So if I come to this module, this means that current node is not full. It might be allowed to just insert properly into this if it is a leaf. If it is not leaf, then I'm going to probably go downwards and ensure that insert non-full is recursively called, provided that node is not full. So insertion will be actually done in a leaf. If it is a leaf node, obviously insertion sort will be applied, insertion will be done, and the corresponding value key, whatever we are supplying the key, that will be assigned and will be updated. Else, I have to go down towards the leaf, and so find proper child pointer to go down. So I will do some logic here to get the proper child. Now I'm supposed to go towards the child I. Going towards child I, if that is full, obviously means I have to go for split child. So remaining on the current node, its ith child to be split. Remaining on the current node is important because the disk access will not be needed for the parent again. So from the parent, the median will be given to this split child. The median will come from the split child to the current node. Hence, all that will handle without difficulty. So split child function will work. X will get split. Now, after this, the child I will get split. So either the current ith child will be the correct direction for insertion, or I plus first will be the child for the insertion. Earlier, it was into the child I. Now it could be, because child I has been split into child I and child I plus 1. So one of these will be the target node for going for insertion. Both are guaranteedly non-full. So in that direction, I will go either I plus 1 direction or I direction, whatever was in this case, and then insert non. Here comes a split child. Coming to this node means X child I is to be split. So split I as child of X, which is guaranteedly full. Of course, I will do the malloc. And in this, I'm going to copy t minus 1 keys. Status of this will be the same leaf as the other node is. And then I have to copy k minus 1, copy t plus 1 to 2t minus 1 keys from y into z. Similarly, if y dot leaf is 0 means it has got pointers of the child also, then accordingly, those many pointers also to be copied from y into z. After that, the median key, which is key t of the y node, is to be inserted into x. So I will be creating a place for the t to come or median value to come, create a place in x. And once I have created a place, I'm going to insert the corresponding key here. So effectively, that means this I will get something like as child I x arrow child I whatever I had. So from child I correspondingly t value, so that meant effectively keys variable and the corresponding index t, this will be the one which will be copied ultimately. So I said shift key and k plus 1 child to create a place. All that shifting will be done, and then the key will be copied plus the left child pointer will be copied, and ultimately I will do all updations, etc. So this is how my insertion can be implemented. Having said that, let's go back and then resume from the current discussion. So here in this, I am doing the insertion logic. So insertion logic will be implemented the way we have done. And now we are going to do the deletion part. So let's go for a deletion logic now. So deletion will be in the parallel lines of insertion. Very similar cases will happen in case of this non-full insertion was easy. So non-empty deletion will be easy. And that is one case. So non-full, non-empty, effectively I mean, non-empty will mean more than minimum keys. Case will be easy. Non-empty and leaf case will be easy. In insertion, we have done sometimes a split. In this case, in case of a deletion, obviously some kind of a merging will take place. So merge will be needed like in insertion needed, but compared to insertion, there is additional requirement also. One extra point, one extra logic needed for deletion. And that case comes because of the reason that delete in an internal node is also possible. Deletion from internal node is also to be handled, which was not the case in case of insertion. In insertion, we always said deletion will happen either into the leaf node, insertion will happen either into the leaf node, or if there is a fullness coming, so we will keep on splitting, but ultimately we will have the insertion done into the leaf node. But if I'm given a request to delete some data from internal node, we have to do that, and this case also needs to be handled. So we will go one by one. Deletion also we will handle through different cases. So effectively we will have 3 different cases, and we will understand what are those cases. So I will say deletion case 1, case 2, and case 3, which I will keep on writing on this slide. And next slide, I am going to show a sample B tree and then understand how those cases come up. So let's assume the same tree which book has used. I'm drawing the same B tree, assuming that t equal to 3. And corresponding to this, I have got values here as C, G, M. This side I have got T and X. This side I have got A, B. Then I have here, let's say D, E, F. For G, I have got J, K, L. So correspondingly, I have got here J, K, L. Here I have got N and O. Before T, the values available with me are QRS. Between T and X, let's assume you have UV. And after X, assume we have YZ. Now, starting, this is my root. So the first thing is, while going through any node, we will ensure that it has got minimum keys. How many minimum? It must have minimum T keys in that node. Why I say T? T minus 1 keys are compulsory at all times. If there are T keys, it will give me a flexibility that I will be able to later merge and give something as a median to the merged node, and still the node will not get disturbed. Again, the aim will be deletion to be done in a single pass. So deletion will be in a single pass, always downwards, go downwards only, never come up. And while going downwards, ensure greater than equal to T keys whenever go down, whenever go to any node. If it is not in anticipation, do that. So solve that problem in advance if the keys are T minus 1. Solve that problem in advance if node to be traversed has T minus 1 keys. So this is going to be the thumb rule. Now start case 1, or I'll say not case 1, I'll say let's start with the simplest case, delete F. How do we start? From the root we will start. Root doesn't mean minimum keys condition. So T equal to 3 means minimum 2 keys always must. Because T minus 1 keys are always must. But we will ensure T keys. So that will mean we will target to have 3 keys every time if we are going. So that later, if out of 3, 1 gets deleted or removed, still 2 keys always remain. So from P, I come to know that F means go this pointer. Now, before coming to this node, I will check, does this node has the corresponding 3 keys, T keys? T is a 3, so minimum 3 keys. Yes, this node satisfies the property. I come to this node. From here, I come to know F. Not in this direction. F is greater than C. Come to this side. F is less than G. Means come to this node. Before coming to this node, check does it has 3 keys? Yes. So I can come to this. Come to this node. This is a leaf node. F is in the leaf node, and leaf node has in leaf node, and node has got the greater than equal to T keys. So deletion is simple. This is the simplest. So this I call as case 1. So I say X, delete. Let's say I'm deleting a K. The requirement is delete K. So I say, if I'm trying to delete K, let's assume that first case is K is in a leaf node, and a leaf node has greater than equal to T keys. So simple deletion, the way we normally do. This will simply mean the corresponding value F to be deleted. Deletion means, of course, if there is some shifting needed of the right keys, etc., some child pointers don't exist because it's a leaf node. So only keys are there. Key deletion will mean simple. Delete the key from the leaf. and adjust your n, etc. from the keys array and n minus minus effectively. Second deletion. Let's say now I want to delete m. So delete m. I start from the root. Starting from the root, I say that m means come this side. From here, I reach to this node. Before coming to this node, let's say this is node x. Then before coming to this node x, I will check whether it has got a minimum 3 keys. Yes. So I am allowed to come here. I reach here, compare C, m is more than this. G, m is more than this. M, yes. This is the value to be deleted. But this means m cannot be simply deleted, because if you delete m, what will happen to this pointer, to this node? This pointer exists, can continue. What about this node at all? I cannot straight away just do that. So that means I take a case 2. Case 2 means k is in internal node. So I am currently at node x. I am at x, at node x, having k, and, or I'll say, if I'm using capital K, I'll use capital K, and k is to be deleted. So obviously, node x has greater than equal to t keys. Because I have reached to this node, obviously this means it is implied. So now k is to be deleted from an internal node, like this. So m to be deleted, and I have to find a solution. So the solution will be that effectively I am going to replace m with either its successor or predecessor if possible. Because replacing m with successor or predecessor will make the things easy. So I say replace m with its predecessor or successor, with its predecessor or successor if possible. The advantage being the whole node structure will not get disturbed. So if effectively predecessor will mean that, first of all, I will go to its previous pointer, previous child. Within the previous child, largest value in the previous child will become the predecessor. In this case, L is the smallest value, but if L has further subchildren, rightmost children, rightmost children, rightmost children, and the rightmost value in the leaf will become the predecessor. So what will be the rule? I say, I take case 2a, if a preceding child, I'll say if preceding child can allow, if that will mean if a preceding child has greater than equal to t keys, means from that side deletion etc. will not be a problem. I will find predecessor of k, say predecessor k dash I call of k, and replace k with k dash, and then recursive call for deletion to k dash. From downwards only, deletion of k dash. K dash will ultimately be a leaf node's data, and there it can be deleted using case 1 later through deletion recursion. But that means I said if a preceding child has greater than equal to t keys. Why did I say? If the preceding child had, by the way, t minus 1 keys, then that problem is to be solved. Only then I can proceed further. So that problem solution will require extra logic. So I don't go in that way. So I will say go and look into the preceding child. For example, in this case, M's preceding child is in this direction. Preceding child has got greater than equal to T keys. It has 3 keys. So I can say, fine, from preceding child, I can get the predecessor. In this case, predecessor is here, but sometimes predecessor can be down. So this will mean effectively that I will be able to say that this will remain P. Instead of this will be called to become C, G, and L. And then because L is coming from this pointer, recursively, I will come downwards to do the deletion. Earlier, here I had J, K, and L. Recursively, I will come this side, and then finally, this will lead to this L to be deleted. So that will effectively mean this value will go, and then I am able to get the current L deleted, L coming here. So this becomes case 2A. Similarly, I say case 2B. 2B will mean similarly, else if succeeding child has got, for example, preceding child could not have this, succeeding child has got greater than equal to T keys, then similar work will be done with the successor. Successor K dash or K double dash to be taken, and that to replace K, and then delete K double dash. You will go for delete K double dash. So this becomes the case 2B. But it might happen that both have only T minus 1 keys. Both have T minus 1 keys. That case we will call as a 2C. If both have exactly 2 minus 1 keys, merge will happen. Exactly T minus 1 keys. So T minus 1 keys of both will become total 2T minus 1 keys. Merge with the help of the corresponding value from the parent. Corresponding middle value. And middle value, that is median value, which is present in the current node. It is present in X. So X is my current node. I'm saying I'm in node X, and my median is present in node X. So X median value will be taken and merging will be done. How? That will be example will be clear. That let's say I have got this data. After this, I had here got already, as per the previous slide, it is NO. So here I have got NO. This side I have got some values. Let's say this was AB, DE. So here I have AB. Here I have DE and this. Let's say now the request came to delete G. Delete G. So that will effectively help me in understanding case 2C. How? I start from here, looking for G to be deleted, go towards this child pointer, coming to this node, allowed or not? Yes, allowed, because it has got 3 children or 3 keys. So perfect, no issues. T is 3, so 3 keys required. Coming here, X, so this becomes my node X. And in this node X, G is present. So X is internal node, and K to be deleted or G to be deleted is present in this. So case 2A, 2 only, case 2 itself is applicable. Then I see, go to the preceding child. G's preceding child has only 2 values, 2A not applicable. Then go for the succeeding child to check 2B, because succeeding child also has only 2 keys, not 3. So 2B also not applicable. So I say 2C applicable. And 2C will mean what? 2C will mean that You have here P already. Earlier you had here CGL. Now out of that G will be removed. It will become CL. This node undisturbed, this pointer undisturbed, else this pointer also not undisturbed. To be precise, shifting will be needed to be done. Sorry, this is NO. So because the indexes will change, so shifting will be done, but ultimately logically this is there. And here now the merging will take place. Merging will mean PE was already here. After this, the G will be put here as a next value. After this, JK will be put. Exactly 2T minus 1 keys will reach here because T minus 1 keys were in the preceding node. T minus 1 keys were there in the succeeding node. So both had exactly T minus 1 keys plus this being median, and this median combined with these two, it becomes the next. And because one value got reduced, one key reduced means one child pointer also reduced. So after merging, one node has been reduced, and that also child pointer not needed in the above node X. So for this perfectly works fine. So this is called as a case 2C. So 2C we have already seen that this is a case 2C where the merging will happen. So similar to insertion, their split happened. Here it's a merging of the children. So I'm doing merging of children so that remaining in the current node, the median can be supplied without additional disk access. So without any additional access, we are able to do that. Of course, it will require disk write also without any additional, or I'll say extra disk access. Disk access are needed, but extra will not be needed. So extra disk access is avoided, and we are able to do this merging. After merging, I will say now do the deletion. So delete G will be ultimately called now, recursively called again, called from X or from X child. So from X downwards or X children downwards. So from X downwards, it will be called. Ultimately, it will mean you will come here. Come here will mean deletion will happen. All this will be deleted, and now you will get G deleted. Keys reduced. So after this, the total number of keys will not be 2T minus 1. One value will reduce, but this is how deletion happens. So going further, at present now what we have got is a P. Then I have got here the corresponding values available are C and L. Then I have here something AB, here something DEJK. After G deletion, this side NO, this side I have got T and X, and similarly all other pointers being available. Now going further, let's say I want to delete D. Again, start from this node. D is supposed to go to this side. Before going to this side, I will check, does it has greater than equal to 3 keys? Answer is no. So I want to go to some child, but that child does not have T keys. So that means that child has T minus 1 keys. So this is a case to be handled. Before the deletion can be done, I have to handle this. So this case I call as case 3 itself. So case 3 means K to be deleted is not in the current internal node. In current internal node, let's say this is called not in current internal node. Let's say that node is named as X. Earlier I said X. So obviously it means go towards some child. Needed, go to some child is needed, but that child has T minus 1 keys. T minus 1 keys. So I can't go down leaving it unadjusted, because later if a deletion from this node happen or because of merging some value gets deleted, this will create a problem. Like maybe, for example, I was trying to delete some value which could lead reduction of value from this itself. Then instead of 2, it will be left with 1 key, and 1 key cannot be, T cannot be less than, number of keys cannot be less than T minus 1 at any stage. So we have to solve that. What is the solution? So the solution now we have to think. So in this case, the solution has to come that ultimately I will try to have a borrow from siblings if possible. If possible. What does that mean? That it has got its brothers and sisters in the adjacent nodes. So case 3a, I say that if sibling has minimum T keys greater than or equal to T keys, 1 key will be borrowed from sibling and come towards this. From sibling, but of course, borrow will happen via parent, via X. X is my current node or the parent, which is the parent. Why we will understand. For example, this case is I'm coming this side. CL has minimum keys. I can't continue. So I will say, look at its a sibling. No sibling this side. So I can't do much from the left side. I look at the right sibling. It also has only T minus 1 keys. So that means that this sibling can also not borrow. So 3A case is also not applicable. So after a few minutes, we will see how 3A case will work. Then I define next case, 3B. Both siblings or whatever, all siblings, if there are more than one sibling. So siblings can't borrow. Sibling, one or many, whatever siblings exist, can't borrow because they have exact T minus 1 keys. Now, as I say, current node also has a T minus 1 keys. Sibling also has a T minus 1 keys. Solution is nothing but merge. Merge along with help of X, along with median, of course. Same thing what we have earlier discussed. So along with median, merging will happen. For example, this is a case, this situation is a case 3B. I redraw on the next screen. I have here P, I have here CL, I have here TX, and then all other pointers available. 3 pointers this side, 3 pointers this side. But I say, going from here, if I am coming to this node, although I am trying to delete D, but delete D will happen much later. Coming to this node is not permitted. So this is going to become X, but X I can't come because neither X has a T keys nor X sibling has a T keys. So even borrow doesn't happen. So I say this is case 3B. Merging will happen. What merging will do? That CL along with median coming from the, sorry, this was a current node X. X is not this node. I am at current node X and I am trying to go downwards child wise, but child wise I am not able to proceed. So I say I will be merging. These CL values were already there. This P value will become the median value at a Tth index at T plus 1 to 2T minus 1. The siblings values will come. This Tx will come. And because there are exact 2T minus 1 keys in this node, I can easily see there are 6 pointers needed, 2T pointers needed, and early also we had here T pointers at this side or T children this side. This side also had T pointers. So those T pointers will, as it is, come here as this. These T pointers will come as it is. So you will have 2 T children properly connected. So now effectively what I get is I got CL PTX, correspondingly all pointers adjusted. Here I have got AB. After this, I have got DEJK, which was one node. After this, L, I have got NO. After this, again something, and something. So once you did this, then now you will again go for delete D call. Again, start from here. This node satisfies, obviously without problem. I'm supposed to go to this child. Going to this child means allowed now because this node has got a minimum T keys. I come to this node, find that D is present here. So this becomes case 1. It is a leaf node. Leaf node has got D and D is to be deleted. Will mean effectively the correspondingly E will be copied at D's place. J will be copied as E's place. K will be copied as J's place. And that's it. And unadjusted child node don't exist. So not a big issue. And effectively case 1 is covered. Delete D covered. So we have not got an example of a case 3A. 3B case we have seen and it worked. Case 3A is still remaining. So we will be able now to see case 3A also. Let's say now I try to delete B. Delete B. So let's go for the last case for today's discussion. Start from here. I start from here looking to delete B. I compare with this C and come to know I am supposed to go to this child. I am supposed to go towards child and this is an internal node. I am supposed to go to the child node. Child has got T minus 1 keys. So this becomes case 3A. I am on some internal node. Value is not in the internal node. And I'm supposed to go to the child having T minus 1 keys only. So this is case 3A. Just see what we wrote case 3A, that I'm supposed to borrow from sibling. Ultimately, first I will say it is case 3 and then 3A. Why? We will understand. So this is, I'll say initially it is case 3. Child has T minus 1 keys. So I'll say go to this. Now go to this is allowed only if I can borrow from my sibling a value. My sibling has got one extra value. Sibling has got T keys. So I say 3A because sibling has got the extra key. Sibling has greater than equal to T keys. So if sibling has got the extra key, now I will be able to use this key. So I just say if I had this particular data and this was my total structure. I'll just correct that so that we can see clearly. So my this is structure and this is the connection. So I say borrow from this. So borrow E will happen, but borrow E cannot directly go this side. So this will mean E will come here. From here, C will be added to this node and E gets removed from here. Removal effectively means that E is overwritten by J, J is overwritten by K. This gets reduced keys because we are not going in this direction. So it is allowed to have T minus 1 keys. But we were coming to this node. This node must have a minimum T keys. So case 3A applied. Here you have got A, B, C. And now you are trying to do the deletion. So borrow done. And now you will say, now delete D, now delete B. So delete B will be now recursively attempted. Delete B means, can I come to this node? Yes, I can come to this node. Coming to this node now, this will mean this will become case 1 because it is going to be the corresponding scenario of deletion from a leaf node without having any problem because a leaf node has P minus greater than P keys or greater than equal to P keys. So deletion of a B will mean effectively B deleted like this. So delete B also works. So effectively, I quickly summarize that I had case 1, deletion from a leaf node, and leaf node obviously had easy greater than equal to T keys. I have reached to this node implies greater than T keys or equal to T keys were guaranteed. Not an issue at all. Case 2 effectively means delete from an internal node. I am currently at internal node from current node, which is internal. So, which is internal, it guaranteed means that this node has obviously minimum T keys, but its children might or might not have, which is an internal node. So case 2 will handle all those cases. So correspondingly, we said 2A, 2B, and then 2C. 2A meant that preceding child has T minus has greater than equal to T keys. So predecessor will be used for replacement, etc. 2B said succeeding child has a T minus has greater than equal to T keys. That will be effectively successor will be used. So I say here it was a preceding child had that. It means both children has exact T minus 1 keys each. So merging will happen along with merge of children with median to be done. Then comes case 3. Case 3 means deletion value K not in internal node, not in current internal node, and go to a child which has T minus 1 keys, having T minus 1 keys. So this needs to solve the problem. Solution will be 3A case, borrow from sibling. If any sibling has greater than equal to T keys. If at least one sibling has extra key, at least one sibling has greater than equal to T keys. And if not, that will be called as a case B, 3B, If not, again, merging will happen. Merging with one sibling. With one sibling, you have to merge. Either left sibling or right sibling, any side you can merge, but current node will be merged with the sibling. And in all these cases, except case 1, deletion will be finally done. Deletion will be done through recursive call after the adjustment. After doing the adjustment. So this is the way my deletion works. For example, I'll give you an exercise that assume initial tree given to you. Initial tree which was given to you, discussed today, of today. For example, we have discussed initial tree having P here, then here CGM, this side TX, and etc. etc. And then think of, say, trying to delete P, then say delete G, say delete X, say delete Z. Try these one by one. First case itself will be the interesting case, and you will understand what is exactly to be done. Bye-bye. All the best to all of you. Let me stop the recording and